Today we're going to start off by going through one more entire example of solving a differential equation. We're looking at second order linear homogeneous differential equations with power series. So let's start with a very simple, but this one's not a constant coefficient one, the very simple second order linear differential equation y double prime minus xy prime equals 0. Now we'll talk about this later, but this is one which, even though it's not constant coefficient, which you can solve, in fact, pretty easily without using power series, but I want us to run through the power series solution as a good exercise. So we're going to start by assuming we have a solution, or look for, not assuming, but we're going to look for a solution of this form. Y is the sum from n equals 0 to infinity of a sub n. Oh, I wrote that incorrectly already. That's a, should be a sub n times x to the n. So I'll fix that here. Then, of course, y prime is the sum from n equals 0 to infinity of n a sub n x to the n minus 1. Again, the zeroth term, n equals 0 term is 0, so if we want, we can shift and write this as the sum from n equals 1 to infinity, and then shift our index to make it the sum from n equals 0, 0, not 10, to infinity of n plus 1 an plus 1 x to the n. Then we can differentiate it again to get y double prime equals the sum from n equals 0 to infinity of n plus 1 times n times an plus 1 x to the n minus 1. And again, the n equals 0 term is 0, so we can start from n equals 1 and then shift the index to get the sum from n equals 0 to infinity of n plus 2 times n plus 1 an plus 2 x to the n. Now, notice here we don't just have y double prime and y prime, we have y double prime and x times y prime. So x times y prime, I'll put over here, and we're going to use this form for y prime. X times y prime is just x times this series, and we can just bring that x into each term and write that as the sum from n equals 0 to infinity of n a sub n x to the n. The idea is that in this differential equation, this is equivalent to writing y double prime equals xy prime. Here's y double prime. Here's xy prime. They're both sums from 0 to infinity. They both are in terms of x to the n, so we can compare them pretty easily. It's always a good idea to write down a few terms just to make sure you're doing everything correctly. When n equals 0, this one's 0. When n equals 1, you get a1 x. When n equals 2, you get 2 a2 x squared. When n equals 3, you get 3 a3 x cubed. And then it continues like that. This one, when n equals 0, you get a sub 2, 2a sub 2, I'm sorry, times x to the 0, which is just the 1. Then you'll get 3 times 2, I'll write it as 2 times 3, a sub 3, x. The next term would be 3 times 4, a sub 4, x squared. Then 4 times 5, a sub 5, x cubed. And we need this series to be equal to this series. There are a few things we can say right away. By matching coefficients, we need n plus 1 times n plus 2, a sub n plus 2. That was the coefficient on x to the n in what we just derived above. That has to equal n a sub n. I'm going to go back. Here's n plus 2, n plus 1, a sub n plus 2 has to be equal to n a sub n. That has to be true for every number n equals 1, 2, 3, etc. Notice that a naught is arbitrary. Sorry for flipping back and forth. Here, A naught is arbitrary because none of these conditions of equating this with this say anything about A naught. And I'll write this down later. It's not just true that A naught is arbitrary, since we get no statement about A naught. This constant term here must be 0 since there is no constant term there. And if this is 0, that means A sub 2 is 0. So A naught is arbitrary, A sub 2 equals 0, and matching all the subsequent coefficients means we need the coefficient on x to the n from one series, the y double prime, has to be the coefficient on a sub n from xy prime. And that has to be true for n equals 1, 2, 3, etc. Let's look at some of the consequences. Well, if we consider only even numbers n, start with, say, n equals 2, you'll have 2a2 equals a4 times 3 times 4. But if a2 is 0, that tells you a4 is 0. And then if you go back here, if n is 4 and a4 is 0, that tells you a6 is 0. And if a6 is 0, that tells you a8 is 0, etc. So the fact that we had a2 equal to 0 and this recurrence relation that tells us how the subsequent coefficients depend on the earlier ones, that tells us that all the even index coefficients must be 0. Now, what can we say about a sub 1? There was no condition on a sub 1, so a sub 1 is arbitrary. What can we say about a sub 3? Well, this equation, when n equals 1, tells us 2 times 3 times a sub 3 equals a sub 1. Put in n equals 2, put in n equals 3 there, and you'll get 4 times 5 times a sub 5 equals 3a sub 3. And then you'll continue this pattern. 6 times 7, a sub 7 is 5a sub 5, etc. If we use each of those to solve for the subsequent coefficients, remember a1 is arbitrary, so we'll solve for all the other coefficients just in terms of a1. a3 is just a1 divided by 2 times 3. a5, let me write this here, a5 will be 3a3 over 4 times 5. But remember, a3 was a1 over 2 times 3. When we multiply that by 3, that cancels the 3, and then we divide by 4 times 5. So we have a1 over 2 times 4 times 5. a7 from this equation is 5a5 over 6 times 7. And what is 5a5? 5 times a5 cancels out the 5, so we have a1 over 2 times 4, and then we need the 6 times 7. This might seem like a very strange pattern, but it continues in the following way, and you can convince yourself that this pattern does continue. a9 will be a1 over 2 times 4 times 6 times 8, and then you'll have a 9 here as well. a11 will be a1 over 2 times 4 times 6 times 8 times 10, the product of all the even numbers that are in this a11 that are less than 11, and then you'll also have this factor of 11 coming in, and they'll continue on like that. Now, with all that information about the coefficients, let's put it together. Remember, a naught is arbitrary. I'm going to use this. Y is, remember, a naught plus a1 x plus a2 x squared plus a3 x cubed plus a4 x to the fourth, etc. A naught is arbitrary. a1 is arbitrary. a2 is 0. I'll just cross those out. a3 will be a1 over 2 times 3 times x cubed now. a4 is 0. The next term is a5, which, remember from right here, is a1 over 2 times 4 times 5, x to the fifth. x6 will be 0. Then we'll have a1 over 2 times 4 times 6 times 7, x to the seventh, etc. And it'll be useful to factor out the a1 here. So I'll write this as a naught times 1. You might wonder, why would I bother that? You'll see that in a minute. Plus a1 times this complicated power series, x plus 1 over 2 times 3 x cubed plus 1 over 2 times 4 times 5, x to the 5th plus 1 over 2 times 4 times 6 times 7, x to the 7th, etc. I put that 1 there because I'm going to call that 1 y1 of x. That's just the constant function 1. And this whole power series here, I'm going to call y2 of x. Well, y1 of x is pretty simple. But basically what I've done here is said, I've found a general solution for this differential equation, y double prime minus xy prime equals 0. And I've written it as an arbitrary linear combination with coefficients a0 and a1. a0 times the constant function 1 plus a1 times this strange function y2 of x. And it's very easy to see that for these two particular functions, if you just write down the Wronskian for those two, the Wronskian is very simple since you have 1 here. Its derivative is just 0. Here of this function, its derivative will have a 1 starting it. The Wronskian will be distinctly non-zero. And so the y1 and y2 constitute a fundamental set of solutions to this differential equation, and this will be, in fact, the full general solution. So I've written that here. Remember, this is a0 times 1. I'm sorry, I'll write this as y1 of x. y1 of x is just a constant function, not 7. 1 plus a1 times y2 of x, where y2 of x is this thing here. Now, here's the question. In general, you might not be able to do anything with that power series. You just have to live with the fact that there's a power series for your solution. You can use a computer and you can get all sorts of information about this power series. You can graph it by taking a very large partial sum of this power series, which will be a high degree polynomial, and look what that looks like. And around here, the power series is centered at 0. So when you look at a large polynomial partial sum, and you look at that in an interval around 0, you'll get a very accurate estimate for what this function looks like. And the larger degree polynomial you use, the better estimate you'll get. It's a better picture of what y2 looks like. But I claim we can actually tell exactly what y2 is just by looking at a little trick here. This might not be an easily recognized series for all of you, but I claim that y2 prime, and I'll just show you the series. When I differentiate this term by term, you get 1 plus, bring down the 3, you'll end up with x squared over 2. The next term, when you bring down the 5 times x to the 4th over this, the 5 will cancel, and you'll have x to the 4th over 2 times 4. Then you'll have x to the 6th over 2 times 4 times 6. Then you'll have x to the 8th over 2 times 4 times 6 times 8. And it'll keep going like that. We can easily write this as the sum of x to the 2n, starting with n equals 0 to infinity. This is x to the 0th power. And we divide on the bottom by 2 times 4 times the product of all the even numbers up to 2n. It might help to remember that 2 times 4 times 6 all the way up to 2n. If you factor out a 2 from each of these, they'll be exactly n2s, so you'll have 2 to the n. And what's left is 1 times 2 times 3 all the way up to n, which is n factorial. So this can be written as a sum from n equals 0 to infinity of x to the 2n over 2 to the n times n factorial. And another way to write that is the sum from n equals 0 to infinity of x squared over 2 all to the nth power. That's the x to the 2n over 2 to the n. And all of that divided by n factorial. Why would I write it like that? Because if that were just an x there instead of x squared over 2, this would be the series for e to the x. So this is exactly the series for e to the x squared over 2. And that's y2 prime, not y2. So what is y2? y2 is the integral of this. And it's not just any antiderivative of e to the x squared over 2, it's the antiderivative of e to the x squared over 2, which happens to be 0 when x is 0, because when x is 0, all of these terms are 0. We can write that in a variety of ways. I'll write it as the integral from 0 to x of e to the t squared over 2 dt. So this function y2 happens to, not just happens, we created it so that has derivative e to the x squared over 2, and when x equals 0, we get 0. So this is exactly our function y2, and of course y1 we already know is just the constant function 1. So that lets us understand the solution very nicely. So I mentioned earlier that we could solve this all without power series very easily, and I wanted to just make sure everybody's comfortable using non-power series methods to solve this differential equation. It's not a constant coefficient one, so the idea of a characteristic equation won't help us directly. However, there's no y term, so we can use a reduction of order. Let's say I let u be y prime. Then this differential equation becomes u prime, that's y double prime, minus xu equals 0. And this is just a first order linear differential equation, very easy to solve. How would we solve this differential equation? Well, we could multiply by the integrating factor. Mu of x in this case equals e to the integral of minus x, which is minus x squared over 2. So we'll get e to the minus x squared over 2 minus x e to the minus x squared over 2. I'm sorry, this would be u prime times e to the minus x squared over 2 minus x e to the minus x squared over 2 times u equals 0. But now I integrate both sides, and on the left side I get e to the minus x squared over 2 times u, that's the antiderivative of this exact form on the left, equals some constant, we'll call it c. In other words, u is c times e to the x squared over 2. Well, what do we do with that? Then remember, u is just y prime, thus y has to be an integral. I'll see c times the integral of e to the x squared over 2. Now, integral comes with an arbitrary constant, so when we write c times this integral, that would be c times some particular value, which I'll call y2 of x, plus another arbitrary constant, which I'll call c1 here. So we have these two arbitrary constants, c and c1, and you have this exact same function, y2 of x, which is an antiderivative of e to the t squared over 2. That gives you the exact same solutions that we found using power series methods, only this one is much quicker and easier in this particular case.